In this problem, we want to construct an enclosure that encloses 400 square feet. The fence costs $1.10 per foot around the outside of the enclosure and 60 cents per foot for the divider. What overall dimensions should the enclosure have to minimize the cost of fencing? Let's start with some possible dimensions and evaluate the cost of fencing for those dimensions. In this case, let's start with an enclosure that is 5 feet wide and 80 feet long to give an area of 400 square feet. The key is to make a diagram of this enclosure with each section of the fence labeled with its length and cost per length. This is useful since it helps us to see that the cost is obtained by multiplying the cost per linear foot times the number of linear feet. The cost of the width components is 1.10 times 2 times 5. The 2 comes from the fact that there are 2 width components that cost $1.10 per foot. The cost of the length components come from the 2 80-foot sections costing $1.10 per foot and the single 80-foot divider costing 60 cents per foot. Putting these components together gives the total cost of fencing for this enclosure $235. Another possible solution is an enclosure that is 10 by 40 feet. Working out the cost of the width and the length components gives a total cost of $134. This is a lower cost than the previous enclosure, which is good, but we don't know if these dimensions minimize the costs. These 2 examples help us to establish the patterns in the objective function for this problem. List those results in a table with the width, length, the cost of the width, the cost of the length, and the total cost. This table can be on paper or in Excel. Continue to add different size enclosures. Note that as the width increases, the length decreases to ensure that the area is equal to 400 square feet. It appears that the total cost is at a minimum for an enclosure that is about 20 by 20. Examining the columns, we see that we can write the length in terms of the width W as 400 divided by W. The cost of the width components is 1.10 times 2 times W. The cost of the length components are 1.10 times 2 times 400 over W plus 0.60 times 400 over W. If we add the expressions for the width components and the length components, we get the objective function. The table helps us to recognize the patterns in the objective function. The total cost can be simplified to yield 2.20W plus 1,120 times W to the negative 1 power. Next, we find the derivative and locate the critical numbers by setting the derivative equal to 0. This leads to a single realistic critical number at approximately 22.56. The first derivative test indicates that the critical number corresponds to a relative minimum. The graph of the total cost function verifies that at a width of about 22.56 and a length of 400 divided by 22.56, these lead to a minimum cost of about $99.28. This matches what we saw in the table too. Not only does the table help us to write out the objective function, it also helps us to verify the correct solution makes sense.